Way back in 1954, a man named Darrell Huff wrote a book called How to Lie with Statistics. It's a kind of a tongue-in-cheek title, and what he did was look at various uses of statistics in advertising, politics, economics, for example, and he tried to analyze the ways in which the presentation of information using statistics can be deceptive. And so his book is not trying to teach you really how to lie with statistics, but really how not to be lied to. And that's kind of the point of this lecture as well. Now, I know, because I deal with many, many students, that lots of students have math issues of some sort or another. And I am sympathetic to that. This lecture will have virtually no math at all beyond simple arithmetic. And I'm not doing a math class, but we are bombarded with statistical claims every day by politicians, by sports figures, by advertisers. And we need to know at least some of the principal ways in which they can be deceptive so that we don't accept bad arguments as if they were good. Okay, so we're looking at statistical reasoning and ways in which it can be deceptive. And hopefully, with just a tiny little bit of math, but hardly any at all, we can be critical about these kinds of claims. Statistics have a bad reputation. Way back in the 19th century, the Prime Minister of England, Benjamin Disraeli, said, "There are three kinds of lies: lies, damned lies, and statistics." And it's interesting that statistics comes third in a progression of lies. And the quote implies that they are the worst lies of all. It's sometimes said that you can argue for anything using statistics. And maybe that's true, but you can't do so honestly. You could be deceptive, but if you're accurately portraying information, it shouldn't be possible to justify any claim whatsoever simply by using a statistical argument. So we're going to look at what statistics are, and we're going to look at some of the fallacies of statistical reasoning that we encounter in daily life. Here's an interesting fun fact that I didn't even learn when I took statistics. The term statistics comes from the word state, and statistics is the use of numbers generated for and utilized by the state. So a couple of hundred years ago, people figured out that when you're running large nations, it's really important to have information. How many people are there in your country? Is the population going up or going down? How much food is being produced? How many casualties were there in the last war? How many members does our army have? These kinds of pieces of information are numerical, and the collection of this numerical data is the origin of where statistics came from. So these were numbers that the state needs to presumably make more rational decisions. Nowadays, statistics are everywhere. They're in advertising. They tell us that one beer has 25% fewer calories than another. Well, that's a percentage claim. They're in politics as we look at polls and we do sampling to try to determine who's ahead in the election and who might win the next election. We see it in sports, especially in sports like baseball, where calculations are being used to help improve the performance of sports teams and to help them win. So statistics have grown from being just information used for running the state and now run just about everything. Almost everything can be turned into statistical information and used for extrapolation and to try to figure out the best course of action. And so this is great. Statistical information is very useful, and it can be a very convenient way to present information. That's not a problem, but there are some problems when statistics are misused. Even though statistics provide a very valuable way of presenting information, they also provide a very convenient way to deceive naive and uncritical consumers of information. And this misuse of statistics leads, whether it's intentional or unintentional, to people drawing unjustified conclusions. And sometimes people are harmed by their misinterpreting or being deceived by statistical claims. The real reason why it's so easy to misuse statistics is that the people who consume this information, and that is us, the public, this public is generally not mathematically literate, and therefore we can be easily misled by faulty claims. It's interesting. If someone couldn't read, if they were illiterate, they would probably view this as a shortcoming and would probably try to fix it. But in our country, people are proudly innumerate. That is, they're proud of their inability to do mathematics, oftentimes. And that strikes me as very odd, because just as you could be misled by a clever speaker, you could be easily misled by the clever use of mathematics in a dishonest way. And so, as part of my critical thinking class, what I would like to do is just give you a few things to pay attention to that are not very complicated, but which happen all the time. And the more you are alert to them, the less likely it is that you'll be deceived by these faulty claims. So here are the ideas we're going to look at in this presentation. We're going to talk about the different meanings of the word average. We're going to look at problems in sampling. Sampling is when you use a subset of a population to draw conclusions about an entire population. How that can go wrong creates problems in sampling. We're going to look at the idea of dispersion in a sample, which is, it's not as technical as it may sound. We're going to look at how pictures can be used to mislead, and then we're going to look at some misleading uses of percentage claims for purposes of comparison. So these are the various things we're going to look at. Like I said, I'm going to try to keep the math to an absolutely bare minimum, and if I can get it down to 0, that's what I'm going to do. The reason why I chose these topics is because as I pay attention to the presentation of information, these are some of the ways in which most often statistics are used to deceive. Let's start with the term average, like the average rainfall in San Marcos or the average salary in San Diego County, the average number of years it takes to graduate from Cal State San Marcos. We use the word average all the time. The problem is the word average is very ambiguous. It has a number of very different meanings, and if we slide from one meaning to another, it is very easy to trick people who don't realize this ambiguity. And so let's take a look at exactly what these meanings are. We use the term average to refer to properties of sets of data. The average tells us something about the central values of a set of data. But the problem is there's 3 distinct ways that average can be measured or talked about. One is the mean, one is the median, and the last is the mode. And they all measure or refer to something different. They're all pretty easy to understand. Once we get the idea of what they mean, I'll show you how you can lie using these ideas. So the mean is the arithmetical average of a set of data. So let's say that we are trying to figure out the average weight of a set of pumpkins. And by average, we're using the mean. Let's say we have 3 pumpkins. One weighs 1 pound, one weighs 2 pounds, one weighs 3 pounds. So we have 3 pieces of data. We add up all the weights. We get 6 pounds. We divide it by the 3 pumpkins. That gives us 2. So the average weight of the pumpkins is 2 pounds. So you add up all the members of the set and then you divide by the number of members in the set. Pretty straightforward calculation. The median is the middle point in a set of data when they're arranged in order from low to high. So in our pumpkin set, the mean and the median are going to be the same thing, because when we order the weights from low to high, 1, 2, 3 pounds, 2 is in the middle, 2 is the median. So it just so happens that 2 is the mean, but it's also the median. This won't always occur, especially with large sets of data or sets of data where the high value and the low value are widely distinct or different from each other. And finally, the mode is the value that occurs with the greatest frequency. So let's add one 2-pound pumpkin to our set. So we've got a 1-pound pumpkin, two 2-pound pumpkins, and a 3-pound pumpkin in our set. Well, the mode of that set would be 2 as well, because that's the value that occurs 2 times. So all of these meanings of the word average are measuring something about sets of data that describe a center point in that set of data, but they're measuring the center point in a slightly different way. So in the example I just gave, the ambiguity in the word average really doesn't matter, because in the pumpkin example, the mean and the median and the mode was all the same value. It was 2. No problem there. However, when the mean and the median and the mode are very different or not close, then the opportunity for deception arises. So let's look at an example where it is possible to be deceptive by taking advantage of the disparity or the differences in the mean and the median and a mode in a given set of data or information. So let's take a look at how we can use the term average to lie with statistics. Let's look at this chart, which represents the jobs in a company, an architectural firm, the number of people who hold each position, and the salary that each person makes, ranging from $30,000 made by a junior draftsman all the way up to $195,000 a year made by the president. Okay, and you also have here the 3 averages calculated. So the senior engineer makes $65,000. That's the mean. That's the number you get when you add up all the salaries of all the employees and you divide it by the number of employees. The senior draftsman makes $45,000. That's the median. That's the middle point when you line up all the salaries in order from low to high and pick the middle value. That's the median. Notice here the mean and the median are quite a bit different from each other. They're $20,000 different. The mode, the salary that occurs most frequently, is $30,000 made by the 10 junior draftsmen. So the mode is the average calculated as the value that occurs most often. Okay, so let's say that a senior engineer goes to the president and asks for a raise. Well, the president could say, well, that's outrageous. How could you possibly ask for a raise? Your salary is $20,000 higher than the average salary in this company. Now, in that case, the president would be deceptive if he didn't mention, or she didn't mention, that the median is the value that is being referred to as the average, whereas the senior engineer is making the mean salary of $65,000. The median salary is $45,000, so it allows the president to make the appearance that the senior engineer is overpaid. And this argument could be even more deceptive if the president were to say, well, what do you mean? You make $25,000 more or $35,000 more than the average salary, and there the average that's referred to would be the mode. So if you disguise whether you're using the median or the mode, you can make it appear as though the senior engineer is actually overpaid. Now, conversely, a junior draftsman, let's say, might go to the newspapers to complain about how the president of the company is overpaid, and could make the argument that the president's salary is, let's see, more than 7 times it's 7 times the average salary in the company. And the president could respond, well, what do you mean? It's only 3 times higher than the average salary of the company. And In those cases, they're both referring to average as a different value. One is referring to the mean and one is referring to the mode. So whenever you hear a claim about average, what you need to ask is, what is that value? Is it the value that occurs most commonly? Is it the middle of the data? Or is it the arithmetical average of the data? And probably for many purposes, the median is going to be a more accurate measurement than the mean, especially when the values between, or the range of values, the low and the high, are very, very far apart from each other. So if you have 11 people in a company and 10 of them make $1 a year and one makes $1 million, well, you can figure out the mean salary is going to be pretty high. It's going to be like $100,000, but that's pretty deceptive, right? Depends on how far the range is between the low and the high. Okay, so the rule is, if someone makes a claim about average, you say, which one? Ask them, which one are you using? What do you mean by average? Now, sampling is a very important part of statistics. It is necessary to draw conclusions about large groups of data or large numbers of people. For example, let's say that we want to figure out how the election is turning out. Let's say we work for a political candidate and this candidate wants to know the chances of winning. Well, we can't ask everybody in the whole country how they're going to vote. That's impossible. So what we do is we take a sample. We take a sample, a small subset of the entire population, and we ask them how they're going to vote. And the idea is, if the properties of the people in the sample are analogous to the properties of the people in the entire population, then the way the sample behaves will be mirrored in how the population behaves and can tell us how the population will behave. So drawing conclusions based on sampling is very important in conducting things like polls, for example. And so therefore can tell us a lot. And they're very, very useful given the impossibilities of assessing large numbers of people's opinions. However, this can also cause problems if the sample is not chosen properly. There's many ways to choose a sample, but probably the most effective way is a simple random sample in which every member of the population has an equal chance of being in the sample. So if we wanted to sample voters in the United States, let's say, then a random sample would choose people randomly from the total population. And the idea is that if the sample is truly random, then the people within the sample will have the same characteristics in approximately the same proportions as the entire population. So if the entire population, let's say, has a median income of $40,000 a year, then in a well-chosen random sample, the median salary of the people in the sample would also have or be $40,000 a year as well, or very close to it. So the sample would reflect and resemble the population. That's a well-chosen sample. There are many ways in which a sample can be biased, and if it's biased, then it doesn't represent the population, and what we extrapolate from the sample will therefore be inaccurate. It won't be true of the larger group. For example, if the sample isn't randomly selected, but is in some way biased, that's going to give us a distorted result. There's a famous case where a magazine wanted to do a poll on the upcoming presidential election, and this was in the 1920s. So they wanted to do a nationwide random poll, and they decided to use telephones to do this. So they called people at random. They got a result that said the Republican candidate was the overwhelming favorite of the voters that were polled. And then the election happened, and the Republican lost, and the Democrat won by a large margin. And so the question was, why was this poll so inaccurate? It was supposedly a random poll. The problem was, it was a random telephone poll. And back then, only wealthy people had telephones, and wealthy people tend to vote for the Republican candidate. So therefore the sample was biased. They thought it was random, but there was an implicit bias built in that distorted the outcome and made it inaccurate. Obviously, of course, you want to have a large enough sample. If the sample is too small, it's not going to be representative of much. This is closely related to a logical fallacy we're going to study called the fallacy of hasty generalization, where you generalize from a sample that isn't large enough to support the generalization. So if you're out walking around San Marcos and you see someone that has a three-legged dog, and you conclude, oh, I guess all dogs in San Marcos have 3 legs, that would be a hasty generalization because your sample is only one dog. It's not large enough to justify the broader claim about all dogs. Psychological factors also come into play. This is important, especially when you're trying to conduct a poll. You have to be very cautious how you word the questions, because sometimes a poll can have a question that people might be embarrassed to answer or to be honest to in response to the questions. For example, if you did a poll that asked people, do you floss your teeth regularly, you would probably get a large number of yes responses. But the large number of yes responses would probably not mirror how many times a day people actually in fact floss their teeth, but most people would probably be embarrassed to tell a pollster that they didn't floss their teeth. And so if that's the case, then the very question is in a way determining the answer, or it's causing the respondent to give a less than honest response. If you see a poll, I think the most important question you should ask is, who's conducting it? If it's a poll that says the Democratic candidate is winning, but the poll is conducted by a Democratic firm, be cautious. If the poll says the Republican candidate is winning and it's conducted by a Republican firm, be cautious as well, because those are groups that have a vested interest in the outcome. And this quotation sums up the idea here. If either the organization conducting the study or the person composing the sample have something to gain by the kind of answer that is given, the results of the survey should be regarded as suspect. And if the questions that are asked concern topics that would naturally elicit distorted answers, the results should probably be rejected. That's good advice. Information about averages may be useful, but we also need to know how the data is distributed, how the values are distributed in a set of data. And so the idea of dispersion, which includes the ideas of range and standard deviation, is really important in statistics. And I'm not going to talk about hardly any of that here, but there is one idea that I do want to talk about related to this, which can give you an idea of why it's important to know. If you take a course in statistics, and I hope you do, you'll learn about dispersion, and you'll learn about things like range and variance and standard deviation and all those other interesting things. I'm not going to talk about these interesting things, but I do want to mention a little bit about range, which is a pretty straightforward idea, at least at this level, and can really be a helpful thing to know in conjunction with average. If you just know the average of a set of numbers, you can be deceived, but if you know the average and the range, you get a much clearer picture of what the data means. If we know the average of a set of data, that's important information, but it can be misleading if we don't know about the range of the data. That is, the distinction or the difference between the largest and the smallest values in the data set. Here's an example to show you how that could be important information. If we don't know the range, we might draw a faulty conclusion. So let's say that you're looking for a place to live that has a mild climate, and you learn that Oklahoma City has a mean temperature of 60 degrees. So the average in terms of the mean is 60 degrees. And you might think, wow, 60 is pretty nice. That seems pretty mild. I might want to live in Oklahoma City. But however, if you didn't know the range, that is the lowest temperature and the highest temperature, that might be a deceptive conclusion to draw, because even though the average is 60 degrees, the temperature in Oklahoma ranges from a high of 113 degrees to a low of 17 degrees below zero. It's actually a pretty radical climate and not a mild climate at all. So knowing the range makes a big difference in how we interpret what the average means. It's not a lie to say that the mean or the average is 60 degrees, but it's misleading unless we know what the range is as well. So that would be an important question to ask. If someone gives you an average, it's important to know, well, what's the range? And that could be a big factor. So for someone to say, the average salary at this corporation is $100,000, that sounds pretty good, right? But if the range is between, most people making $1 and the president making $10 million, that's a pretty big range, and that grossly distorts what the average actually refers to. So you have to get the range as well. Graphs and pictures are often used to present information, and when done well, they can present information that is very complex in a way that is very easy to understand and clear. But graphs and pictograms, that is the pictorial representation of data, can also be misleading in a variety of ways. And here are some examples of how graphs and pictures can be misleading to present data. So you get your first job and you're making a good salary and you want to start investing in your 403B and your Roth IRA. And so you go to an investment counselor and the counselor shows you this picture of a corporation you should invest in. Look at the amount of profits over time. The problem with this picture, with this graph, which is intended to be misleading, is that it doesn't have a scale. It's a sharply rising line, that's true, but we don't know how long it took for that line to rise. We don't have any values on the time axis, and we don't have any values on the profits axis either. It makes a big difference if the profits are being measured in degrees of tens of millions of dollars or in tenths of a penny, right? If we don't know what that value is, then we don't know what this graph means. So beware of graphs where there's no scale. Even if the graph has a scale, as do the graphs here, you still have to be cautious that the graph is not what we call a chopped off graph. A correctly constructed graph begins at the 0 point. If you look at the figure on the right, which is figure 12.7, this is a correctly constructed graph because the vertical line and the horizontal line both start at 0. The graph on the left, which is supposed to represent the same information, does not start at 0. It starts at 8. And so therefore, it makes it look as though the profits are rising very sharply during the 4 quarters of 2013, right? Because that line looks very sharp. However, when the graph is correctly drawn, as it is on the right, you see that this is the same information, right? The profits going from 8 to 10 million. This is the same information, but you can see that the line is much less dramatic. So when the graph is chopped off, it allows a deception because it looks as though a more extreme result is occurring than is in fact the case. So here's an example of a chopped off graph from real life where a person claims that after a long period of economic stagnation, an election took place, and then shortly after that election, a skyrocketing stock market began. But the problem is that this graph does not begin at 0 and does not present the information accurately. So now here we have the chopped off graph on the left and an actual accurate graph that goes to 0 on the right that presents the same information. And when we look at the graph on the right, which presents the same information, what we see is a period of about 8 years of steady economic growth that is continuing after the election. If we just take the isolated portion that is in gray, it gives the impression of a dramatic change, whereas what was actually happening is simply a continuation of what had been happening for the previous 10 years or so. So beware of chopped off graphs. So here the graph on the left, which represents Yankee baseball ticket prices leveling off, is intended to show that after a radical increase in ticket prices, now they are flat and they haven't been doing any growth. The problem is this graph is incorrect. The horizontal axis should be the axis of time, whereas in that graph on the left, time is put on the vertical axis, the up and down axis. When the information is correctly presented with time on the horizontal axis, what you see is, in fact, that over time there was relative stability in ticket prices and then a dramatic escalation. So the time factor needs to be along the bottom on the horizontal axis of a correctly constructed graph. You have to be cautious when people are using pictures to present information. It's very easy to be deceptive. The figure at the top accurately represents a doubling of oil production over a period of time. The double production is represented by 2 oil barrels of the same size. There's nothing wrong with that pictorial representation. The pictorial representation at the bottom would be a distorted picture of a doubling of oil production. Yes, the oil canister on the right is twice as tall, but it's also 600% larger in volume. So it's actually much more than twice as much. And so it gives a distorted picture of what's actually occurring. We hear percentage claims all the time. The problem is that sometimes percentage claims can be deceptive, and we need to be careful in interpreting them. When percentages are used to compare values or compare situations, here we have to be extremely careful as well. Here's an example of what I'm talking about. So for example, if someone says that Zesty Cola has 20% fewer calories, and you hear this claim or something similar made all day long every day on television, the question we need to ask is 20% fewer than what? If Zesty Cola has 20% fewer calories than another cola, that might be good news. But if Zesty Cola has 20% fewer calories than, say, butter, that doesn't mean it's actually very much better for you. So this is what we call a dangling comparison. By saying it's 20% fewer without telling us what it is being compared to, then we don't know what the value means. When someone makes a claim of a percentage change, usually a very dramatic percentage change in something, you have to ask how many things are being used to calculate that percentage. Because if the number of things, or the base, is very small, a little change can cause a dramatic increase in the percentages, and that can appear to be deceptive. So for example, if the number of COVID-19 cases in San Diego County goes from 1 to 2, well, that's an increase of 1 person, 1 case. But in terms of percentage, it's 100% increase. And so you can imagine somebody wanting to be deceptive could claim that there's been a 100% increase in COVID cases, and that sounds extremely dramatic, but it's also extremely deceptive because the base is very small. So don't be too fooled by percentage claims unless you have some knowledge of what the base is that's being used to calculate that percentage change. You won't find the up to fallacy in any book or any website that I know of, because I'm the one who invented it, and I'm very proud of having discovered this. Once you learn the up to fallacy, you will see it everywhere. It's almost impossible not to see it. And here's the basic claim. an advertiser says, at our amazing one-day blowout sale, you could save up to 40% over our competitors. Just watch any 5 commercials on television. I'll bet you 3 of them will say this. Now, the problem is the claim is meaningless because it might just mean that a couple of items in the store are marked down 40%, but the rest of the prices stay the same. Or they could even go up, and they're still telling the truth. It's possible that you could save up to 40% if you pick the magic items that are marked down, but it's more than likely you're not going to pick those items, so it's a fake sale. And don't forget, when someone says save up to 40% and you only save 1%, well, technically they're not lying because 1% is up to, it's on the way up to 40%. But it's also a lie. So watch out for this fallacy. Here's a couple of examples. So here's some stuff from my mailbox. One A Day Vitamins says that up to 90% of Americans fall short in getting important nutrients from food alone. So my question is, well, how much up to 90%? Is it 5% or 10% or is it 89%? It makes a big difference. Up to 90%, that's a pretty big range and pretty vague. If you shop at Smart & Final here in San Marcos, you could save up to 16% every day versus your current supermarket. So at least they tell you what the percentage is being compared to, right? They didn't just leave it as a dangling comparison. They didn't just say save up to 16%. 16% over what would be the question. However, they did commit the up to fallacy because even if I save 0.001%, that's up to 16%. It's in that range of savings, so it could be a meaningless or deceptive claim. Or, again, it could be deceptive in the sense that maybe one item in the store is marked down 60% and all the other prices are the same as they usually are, or they could even be higher and the claim could still be true. So, yes, I know, I'm eccentric. I read the crazy stuff that comes in the mail, but the point is that these are acts of deception that you may not recognize unless you have a little bit of information. But once you get a little bit of information, then you have a little bit of power and you become much harder to fool. And if we're harder to fool, then maybe things in the long run will get better for everybody. So we're almost at the end here. I just want to conclude with a few quick, short errors to be aware of that happen all the time. You should be aware of spurious accuracy. These are claims that represent accuracy of figures that are so astonishingly precise that they couldn't possibly be known with any certainty. Like if someone on the city council says 342,612 pounds of diapers were dumped in the county's landfills last year. The question is, how could that person possibly know that figure to that degree of precision? And the answer is they probably couldn't. So also you should be aware of vagueness. Lots of terms are thrown around that mean virtually nothing unless they are very precisely defined. Things like poverty or intelligence or popularity. What are these referring to? What are they measuring? How are these measures being ascertained? It's very easy to be ambiguous about these claims and deceptive. You have to be careful of cherry-picked data that discards data unfavorable to one's intended result until the desired result is achieved. So let's say, for example, that I'm a vaccine researcher and I'm really, really anxious that my vaccine be approved for COVID-19. And so I administer a test, and yet I only count the data where the people improved, and I ignore the data that doesn't really support my conclusion. That's called cherry picking. When you're cherry picking, you only pick the best cherries, right? So if you're cherry picking data, you're only picking the data that supports your claim. The problem is that's totally dishonest and deceptive. The last thing I'll leave you with here is the idea that correlation does not necessarily mean causation. Okay? Just because two things are found together very frequently doesn't mean that one is causing the other. We tend to think that this is the case, where one is found, the other is found, so one is causing the other, but a little bit of thought says, well, maybe sometimes that's true, but maybe sometimes it isn't true. For example, peanut butter is often correlated with jelly on a sandwich, but that doesn't mean that peanut butter causes jelly or vice versa. So be careful of these claims that something is causing something else merely because they are correlated. All kinds of things are correlated with each other, but we wouldn't want to say that one is causing another. Here are some examples of that. For example, the number of people who drown by falling into a swimming pool correlates with films Nicolas Cage appeared in. You can see that the two lines graphed are very, very closely aligned. They're very closely correlated. But we wouldn't want to say that Nicolas Cage films cause people to drown by falling into a swimming pool. The two things are correlated, but there's no plausible causal connection between the two. So the final word goes to H.G. Wells, who said, "Statistical thinking will one day be as necessary for efficient citizenship as the ability to read and write." And he's correct. And we have reached that day. And so it's time for us to improve our statistical thinking as it is to improve our ability to read and write and also to think critically. And hopefully this has been a small step in that direction for you. And hopefully it was painless, not too many numbers. And I hope you got something out of this. And we'll see these fallacies and these errors in your everyday lives where you wouldn't have seen them before. And if you do, then I've done a good job. So take care, and I'll see you in the next lecture.